Hello friends, welcome to this tutorial and survey on extending English large language models to new languages. This is kind of a very interesting area these days with all LLMs coming up and a lot of English LLMs, but then also a lot of interest in multilingual LLMs. So that's where this tutorial is situated. How do we take these really good English large language models and then make them, adapt them to work for new languages? So let's go over the outline of what we will cover today. So first we'll have a small introduction to LLMs to set some context, and then uh, talk about why building multilingual LLMs is a challenge. And then we'll cover the main part of the tutorial, which is about extending English LLMs to new languages. And we'll go over various stages of this process. And finally, we will summarize the learnings and some possible future directions of work and research in this area. So all the material for this survey will be available on the GitHub page, and there is a bibliography that we'll keep maintaining so that it is up to date. So let's get started. Mm. So first of all, what are large language models to sort of set the context for this discussion? So these days, when we say large language models, it generally means transformer decoder models. And so these are uh, neural networks that generate text by looking at only the previously generated context. These are autoregressive models. And they basically learn a model of the language in terms of learning to predict what word comes next given the previous word. And how are these models trained? So these are not trained on in labeled data, uh, but mostly on unlabeled data, which is essentially textual data. And so the training task is a self-supervised task. So given a lot of monolingual corpus, learn to predict the next word given the entire context. And this context could be a sentence, a document, a paragraph, etc. Typically, you want to learn as large a context as possible so that you can learn a lot of correlation amongst words and concepts. Okay, so what makes large language models interesting is that they are trained on this very simple self-supervised task, which is next word prediction, but coupled with training on a humongous amount of textual data and on large models which have a lot of parameters running into billions, which give the model enough capacity to learn wonderful correlations between a lot of concepts that are present in the text. So that's what makes these large language models interesting. And then they imbibe the models with this interesting capability, which is the capability of in-context learning. What that means is if you present the model uh, a few examples of a task, the model is then able to understand the task and then given a new input, perform the task. As an example, what you can see here is an instruction, a task of sentiment analysis. So if you give the instruction about tell me the sentiment for this review, and then two examples, right? So the first example is of a positive sentiment, where the sentiment is indicated by a word like the movie is great. Uh, and the second example, the sentiment is indicated by pathetic. Now, if you give it a new prompt, a new input, which is it is just a rehash of old movies, the movies is, and then ask the model to predict the next token, it will predict the right sentiment. That's the hope, right? So that's an wonderful capability. Of course, in context learning capability is not sufficient. It's powerful, but it's not controlled, and therefore, typically, large language models have to be fine-tuned on a relatively small amount of supervised data and preference data, where human preference of among multiple possible outputs are provided to the model. This allows the model to be aligned to instructions and to the values that you would want the model to follow. So you would not want the model to generate hate speech, etc. Right? So that's what this process of fine-tuning and preference alignment ensures. Now, these current generation of models, starting with GPT and then Llama and other models, they are different from the older generation of models, which by which I mean models like BERT or BART or XLMR. So how are they different? So in the current set of models, every task is just text completion, right? Whereas with the older generation, you would have a general pre-trained model, but then you would have a classification head or a text or a fine-tuning process for text generation, etc. Uh, the current models are mostly decoder-only models only, and they do both NLU, natural language understanding, and NLG, natural language generation. Whereas the older generation of models were either encoder only or encoder decoder model, depending upon whether you want to do NLU or NLG. Uh, with the current models, they rely a lot on in-context learning and instruction tuning, so as to perform a certain task. Okay, so they're not particularly trained for one task, but the model is capable and powerful enough to do a lot of tasks. The in-context learning or instruction tuning helps to align the model, make it understand instructions, and align to values. Whereas earlier we used to do this pre-training once, and then for every task you would fine tune it with supervised data for that task. So that's an advantage that these current LLMs have. We're mostly doing causal LM modeling currently, whereas earlier we were doing mass language modeling or denoising auto encoder objectives, which were denoising objectives. The models these days are large, so as to learn patterns from a lot of data and make interesting correlations between and to be able to perform a lot of interesting tasks. Whereas the older models were mostly much smaller, uh, good enough to do pre-training and understand the language, and then be able to fine tune for the end task. So that's that. Those are like the major differences. The last difference being, of course, the amount of data that these are trained on. Llama 3, for example, is trained on about 15 trillion tokens, whereas BERT was trained upon 137 billion tokens. So there is a huge magnitude of difference in the amount of training data that was used to train these models. So what makes these LLMs exciting? So they've been trained a lot of data, and therefore there's a lot of inherent knowledge in these models. Because of these, they can do a variety of tasks, as you can see from the kind of examples on the right hand side, be it question answering, grammar correction, summarization, translation, say text to command, parsing unstructured text, understanding code, generating code, etc. Right? And you can give instructions to do compose different tasks. Maybe you want to generate code and then explain it, or generate code for generating a plot and then so on. Uh, but there is very little task-specific training, right? These are mostly coming from the inherent capabilities of the model, with a lot of pre-training the model has been done on, and post-training helping to align the model to certain instructions and preferences. And so you can see the wide range of tasks, be it writing, creativity, brainstorming, data generation, explanation, etc. That's what has sort of generated all this excitement about LLMs. And there are these wonderful examples from this paper, Sparks of AGI, which you should look at, where you can see that the model can sort of say do math or math plus poetry, or it can generate code for plotting. Uh, it can explain code, understand programs, uh, etc. Right? So that's the wide range of possibilities that has generated all this excitement with large language models post the release of ChatGPT. And because of that, there has been an explosion in the work on LLMs. A lot of LLMs have been released, uh, both proprietary models like OpenAI, Anthropic, Gemini, Mistral, and Cohere are a mix of both open source and closed source. Uh, then there are many other open source models like Llama, Gemma, Phi 3, and those are some of the smaller language models. Uh, they have spawned their whole set of research LMs. Say, for example, Llama has resulted in a lot of models like Koala or Lava, Open Flamingo, uh, Chinese Llama as multilingual extensions, etc. However, most of the work has been limited to English. There's a lot of progress on the English LLM front, but the gains for non-English languages have been limited. And so that is what we will try to see in this survey as to what is happening on the work on the non-English language front. Uh, So, just to put this in perspective and in terms of some quantitative numbers, the benefits of all these LLMs have been mostly limited to English. So, if you evaluate, for example, ChatGPT and its performance on different languages, uh, so you can see that the English performance is much better than any other language. So in this slide, you can see results on the natural language inference task, which is a classification task, CSQA, which is a common sense question answering task, and X squared Q&A, which is again a general purpose question answering task. On all these tasks, you can see that the gap between English and all other languages when you use ChatGPT for these tasks is quite substantial, and therefore uh, there is a substantial effort required to close this gap and bring these non-English languages at par with English, and to get the benefits of all the benefits that large language models have been providing uh, for all these other languages as well. As an additional example, let's look at translation, which is a classic cross-lingual task. So the two uh, tables on the right-hand side, you can see that the performance of ChatGPT is much inferior to an open source specialized translation model like NLLB, or even a proprietary translation model like Google's machine translation model. And there is a substantial gap to be uh, covered, and particularly uh, if you see the table on the right hand side, the gap for high resource languages is lower, but the gap for low resource languages, which is the upper part of the table, is quite substantial. So what people have seen is that when it comes to LLMs, their performance is typically good for high resource and languages which use Latin script. The For low resource languages, and particularly those which don't use the Latin script, the performance is not as good. And therefore, like a strong baseline is always just to take the input in whatever language you're working with, translate into English, and then feed it to the LM. Right? And so these are results with ChatGPT. Open source models lag behind GPT models also, because GPT at least has some representation presumably of other languages, but most open source languages, at least to begin with, have been focused mostly on English only. And now, like, we're seeing some open source model getting some representation in non-English languages as well, but there is still quite a way to go. So now the question is, why do these LLMs lag behind for other languages, right? So one is, of course, you have a bunch of reasons. So one, the lack of pre-training data. Mm. So English data clearly outstrips data for any other language by far. Uh, and particularly for low resource languages, the data available on the web is very less. As an indicator of that, you can see the Wikipedia sizes of major languages, some representative languages, and you can see that English is by far way ahead, and that is the situation, the general scenario on the web. Now, reflecting this data availability, most LLMs are trained with a large amount of English data, and most of the high performing top LLMs have less than 10, and that is also a very liberal number. I mean, most of the non-English data is way less than 10% in most of these LLMs. Then, because English is given primacy, the token representation, the tokenizer design also reflects that. So most of the token space is assigned to English tokens. You can measure this representation by using this metric called fertility. So fertility means number of tokens per word. Uh, and so the lower the fertility, the better it is, because then you can efficiently encode the tokens in a language. And also, like, uh, it presumably means that these tokens are meaningful and you can learn better representations. Now, if you look at the table at the bottom, you can see that the fertility is very low for English. It's typically between 1, 1 to 2, mostly less than 1.5 for most LMs. And for most high resource languages, and specifically for Latin script languages, that trend holds. But you can see that, say, language models like GPT have a very high fertility for languages like Telugu, Malayalam, Tamil, Bengali, most Indian languages that you can see on the right, or even for Greek and Thai, which also use non-Latin scripts. So what that results in is very low efficiency, because you need more tokens to encode the same amount of text. And also, like, learning representations at character or near character level or even sub-character levels is suboptimal. You might not be able to learn high quality representations. It's just like pre-training data, the next limitation is that the amount of instruction tuning data is very limited. And the next step is, of course, generally you want to have human preference alignment, and that data is even more scarcer for non-English languages. Given all that, then we want to rely on the ability to transfer knowledge from English to other languages, and that is a very open problem. Transfer happens to some extent, but it is a very open research problem as to how do we do even better. Transfer is more challenging in decoder-only transformer models compared to word-style encoder-only models, where transfer was much easier, and therefore you could see a lot of zero-shot uh, uh, cross-lingual transfer when the models were trained only on English, but it's more challenging when it comes to generative models. Uh, so as I said, one strong baseline is translate test. You can always translate your data into English, run it through an English LM, get the output in English, and then translate back. So the limitations, of course, are the quality of the translation models. Not a lot of models have very high quality translation. Uh, and even with those that have high quality translations, there are still gaps. Particularly, most MT models don't work with large context. They're mostly limited to sentence level context, and therefore, a lot of knowledge might be lost when translating. Having said that, the question to ask is, do these English LLMs still have some inherent multilingual capabilities? And the answer to that is yes, there is. So why is that so? One, of course, these models are trained on a lot of English data. They learn a lot of world knowledge, which is kind of language agnostic. So the models do learn a lot of knowledge. But then are these transferable to other languages? And so as I said, they are to some extent. And why is that so? One, because during training, they might have been exposed to some non-English data, because you might have documents that are written in multiple languages, English plus some other language, and these might be part of the training mix. Or maybe an incorrect LID resulted in uh, data from other languages also creeping into the pre-training mix. And increasingly, like many models are getting some representation of non-English data. For example, the latest Gemma 2 and Llama 3 models do have representation, multilingual data represented. Although, as I said, it is like way less than English, less than 10%. Right? But the question is, how good are these multilingual capabilities? So broadly, you could say that these models may be okay at language understanding, say tasks like classification, sentiment analysis, but the generation is not good at all. In fact, it's bad. Uh, they might still be okay for Latin script languages, but bad for non-Latin script languages. And it's finally a function of how much pre-training data in these languages the model has seen, and typically very less. Most of the data seen is in English. The next question is, okay, whatever language multilingual capabilities these models have achieved, how do they achieve it? So the hypothesis, one of the hypotheses is that do these models kind of think in English? So they consume input in one language, output in another language, but then do the internal processing in English. Put it in another way, do these LLMs use English as a pivot for decision making, right? So uh, there are a few studies which sort of arrive at this broad consensus that the lower, if you look at this table on the diagram on the right, the lower layers of the model, the lower layers of the model sort of do understanding, and there are language specific components here, but um, uh, in the process, as you move up these layers, some sort of language agnostic representation is learned. Uh, but there are these languages essentially deal with language specific concepts and moving towards language agnostic concepts. The middle layers are generally the problem solving layers, and these tend to have a bias towards English representations. So the models are thinking in English, uh, and specifically, it said that the self-attention layers do the thinking, and they are biased towards English, whereas the feed-forward networks encapsulate the knowledge, and this could be from English or from other language sources as well. Finally, the top layers are responsible for generation, and they generate multilingual. They are specialized for uh, different target languages. They again have language specific neurons. So broadly, that's what you would see. The bottom layers do some feature learning, learn language agnostic representations. Middle layers do concept mapping, task solving, but there is an English bias, and top layers are specialized for language generation. And you can identify these language specific neurons through certain studies, and these are mostly concentrated in the top and bottom layers. So the central question when building multilingual LLMs is how do you bring the representations of other languages closer to English, and the better you can do that, the better you can do cross-lingual transfer. Another illustration of how this processing, multilingual processing is done is in the diagram on the right, which shows the at different layers what are the most frequent tokens. So this is the next prediction problem. The last column is the next word to be predicted, and you can see that the bottom layers have a mix of tokens in different languages. In the middle layers, you can see English, and in the top layers, you can see the actual target language, which in this case is Chinese, is the most likely token. So that sort of shows very interestingly what's happening in the network during processing. Uh, so next, let's look at how do we uh, so now let's look at the landscape of open source multilingual LLM efforts. So there are broadly two categories of models. So one is these models that are trained from scratch with English and multilingual data. So Bloom was probably the first major effort from the Big Science group, but then there are many other efforts like MGPT, PolyLM, Eagle, MT0, etc. And amongst the major ones, I think now Aya and Llama 3, Gemma 2 are getting some multilingual representation as well. Uh, so here the problem is that the English representation could be less compared to models like English heavy models like Llama, Gemma, Mistral, and therefore their uh, English capabilities might be inferior. And if that is the case, then that would also impact performance in non-English languages. And to do this training for multiple languages needs large-scale compute. The other direction to look at is to take a English heavy LM like Llama, Mistral, or Gemma, and then extend its capabilities, adapt it for new languages. So there are different examples of these like Chinese Llama, OpenHati, CLLM, uh, Alma, Roman Setu for different languages. So OpenHati is for Hindi, CLLM for Southeast Asian languages, uh, and Roman Setu for a bunch of Indian languages. So here, the advantage is that these models already have strong capabilities in the base LLMs for English, and we can build on top of that, and therefore extending to other languages might require less compute. Plus, we make use of the already existing English capabilities of these base LLMs. Plus, these English LLMs evolve fast. There are many new models, state-of-the-art models coming up every day, and it's much easier to adapt these models to new languages and to get the benefits of the latest in the English LLM space than to be able to train multilingual models repeatedly from scratch. And so that's what we'll focus in this survey, where we will focus on how do we go about extending English LLMs to non-English languages, all the work that has happened recently in this area. So the broad recipe for extending English LLMs to non-English languages is, well, we start off with an English LLM. And because these might not represent the vocabulary, the tokens in a new language, we first perform vocabulary expansion, add new tokens to the LLM. Uh, and once that is done, we then uh, continue pre-training the language model with monolingual corpus from the language, new language that we're interested in. we do instruction fine-tuning in the new language, followed by human preference alignment in the new language, uh, which finally gives us our multilingual LLM with English and the language that we are interested in. So let's go over these steps one by one. So the first step is vocabulary expansion. So let's understand this. Uh, so first, let's understand the basics of vocabulary as it applies to language models. So if you have a word like spacecraft, the language models do not consume the words as it is. They decompose the word into tokens from the vocabulary of the language model. So that's what the tokenizer does. So in this case, spacecraft might be broken into space and craft. And each token uh, has associated with it an embedding which captures the semantics of the token and its relationship to other tokens in the vocabulary. So for example, you can see that this sentence here is tokenized into multiple smaller units. Uh, and these set of the unique set of tokens constitute the vocabulary of the language model. Now, what are the properties of the language model's vocabulary? So it works with a finite vocabulary, and therefore, the vocabulary is at the subword level. So the vocabulary units are smaller than words. These two properties combined result in an open vocabulary. So all words can be broken up, can as a decomposed as a concatenation of the subwords that are part of the LLM vocabulary. Now, what happens if the tokens in your language, the characters or the words in your language are underrepresented in the vocabulary? So what happens is then very aggressive tokenization will happen. So you can see the same English sentence translated into Hindi, and the way the same tokenizer tokenizes. In this case, this is the Llama tokenizer. So you can see that here the words are almost broken down into characters and sometimes even bytes. So these sequence of 0x, E0, etc. These are bytes. So because Llama tokenizer is a uh, BP tokenizer with byte fallback, if the character doesn't exist in its vocabulary, it just backs off to bytes. So what happens because of this, right? So if you use BP based vocabulary and some characters don't exist, you just replace them with unknown vocabulary items, which is loss of information. If you're using um, uh, if you have known characters, but then you almost back off to characters, then you have very high fertility, which you can see here, right? So almost every word is broken down to characters. So the fertility is very high. Uh, in case these are byte-based BP, then the unknown characters are essentially broken down into bytes. Now, most Unicode characters are like 2, 3 bytes, the variable length, and so you have even higher fertility, right? So it's not a good idea because this high fertility results in more memory consumption because now attention over the entire sequence will require more memory, more decoding time because the sequence length is longer, and it puts a limit on the longest processable sequence. Now you cannot process as long sequence of text as English for the same content because the fertility is very high. You need a lot more tokens to represent the same information. And therefore, how do we address this issue? So one is, of course, we can work with the status quo. We work with suboptimal vocabulary, and you saw the limitations: high fertility, increased sequence length, inferior representation. But because the model has been trained with some sort of inferior representation, maybe you need less pre-training to sort of adapt it to a new language. But at inference time, you have all the limitations we just discussed. The other option is to extend the vocabulary. With the vocabulary expansion, you can achieve lower fertility, reasonable sequence length, but yeah, you would need more softmax computation because the vocab size has increased. That might not be a big penalty to pay, but you might need more pre-training so as to align the new language to the already trained model, which works well with English. And there is some evidence to suggest that you might need to do a lot of pre-training to align the language model well with the existing the new language with the existing language model. Although this is variable, I think there are different studies with different numbers. You might just need a modest number of training as well as per some studies, but still like more than what you would want to do with the original vocabulary. Okay. So next, so how do we extend the vocabulary? So what we can do is to first take monolingual data in the language, train a tokenizer using some standard tokenizer like the BP algorithm or the sentence piece uh, library to train Unigram or BP models. With that, we get a new vocabulary. We concat that with the existing vocabulary to obtain the extended vocabulary. Of course, this is just the vocabulary, but then the new vocabulary items also need to uh, have embeddings. So you need to initialize the embeddings for the new tokens. So once that is done, we can uh, have a base LLM which is adapted to have new tokens and their corresponding new embeddings. And this is the starting point for then now building up our new uh, extended language model, multilingual language model. But now how do we do these steps? Particularly, how do we initialize the new embeddings? And there are a bunch of methods to do that. So the simplest thing is to just randomly initialize the new embedding. Uh, but this can change the existing vocab's probability distribution. And therefore, if you want to continue to pre-train with uh, the new adapted model, the convergence time might be higher. And very simple idea is to initialize the new embeddings with the average of existing embeddings of the existing tokens. Uh, so averaging has a good property that it doesn't change the existing vocab's distribution. And but still there are no guarantee, and so the existing language English performance will not be impacted, but there's still no guarantees on the convergence time. But if you could smartly uh, uh, initialize the new embeddings, for example tokens which are similar to tokens in the existing vocabulary, uh, that can help improve the convergence time. So there are a bunch of methods which do this by doing a weighted average of the existing embeddings. So the more similar embeddings have higher weights and so on. And a bunch of these methods essentially can help to reduce the convergence rate. Uh, there are recent approaches also about hypernetworks to learn embedding. So these are little models which can take in a token and then predict its embedding. And the models, these networks are trained in such a way that they can predict embeddings for any tokenizer for a given fixed model. Therefore, sort of enabling zero-shot tokenizer transfer. So you can just swap out a tokenizer and bring in a new tokenizer, predict its embeddings, and with a little bit of pre-training, get back the performance of the original model. So those are interesting directions. So just go through some details of these. So average initialization. Uh, so this sort of tries to rectify some of the limitations from random distribution, random initialization. So random initialization can do incorrect generation for existing language also, and therefore you might need a lot of continued pre-training to get back to the older performance. So what you can do is initialize the new tokens as average of embeddings of existing tokens. What this results in is a low KL divergence between the pre and post expansion LMs for the existing vocabulary. Uh, and in fact, you can show a stronger result that greedy decoding with the prefix of existing tokens will result in exactly the same output from the existing tokens. And in fact, uh, kind of a stronger result, a more general result is instead of averaging, if you just ensure that the embeddings of the new tokens uh, are in the convex hull of the existing embeddings, uh, then the existing the generations of the existing tokens, they don't change. Right? And so this is a very practical solution. So we can just do an averaging, and uh, maybe a little noise can be added, a little random noise to these average embeddings, so that every embedding is slightly different. Uh, Practically, this doesn't seem to affect much, although there is no guarantee now that these models are now in the convex hull. These embeddings are in the convex hull of the existing embeddings, but a small random noise probably makes very little difference. So in practice, this works well. So when you do this kind of average initialization, we do see a initial drop in task performance on doing continual pre-training compared to the original vocabulary. But this performance drop decreases, the performance increases as you bring in more training data. And of course, you get the efficiency gain that you have with a with a better tokenizer with more vocabulary items. So broadly to summarize, this strong baseline. However, this method doesn't give any solution to improving convergence in continued pre-training. For that, as we just discussed, there are these methods based on weighted average initialization, and the key idea is that these target token embeddings are weighted averages of source token embeddings, and the token weights are based on similarity between the source or the original uh, tokens and the tokens in the new vocabulary. Now, how do we get these similarities? Typically, these are based on some external static pre-trained word embeddings. So for example, this method called Beshel, what it does is, if you see the equation here, the existing embeddings are, the new embeddings are represented as weighted averages of existing word embeddings. And these weighted averages are these numbers SXY, which represent similarity between the uh, new token and the older token. And one way to look at it is if you had uh, token embeddings, static token embeddings for these old and new embedding spaces in the same space, then you could just compute cosine similarity between the token embeddings. And so uh, there is a lot of older work on aligning word embedding spaces using libraries like Muse, and you could get these similarities between tokens in the same aligned space. So if you can do this, then you can achieve faster convergence in terms of LM perplexity as well as performance on downstream tasks. Most of these results, of course, have been shown on on large LMs. Do you really get such convergence when it comes to large LMs? That's kind of not very clear. Uh, there are some extensions to these methods, the simple averaging method like UFA. So UFA is an extension of Veshel, where you want to work with multiple languages and multiple vocabularies, and therefore some optimizations are done. So one is reducing the dimension of the embeddings. This is inspired from the Albert language model. So you basically factorize the embedding matrix into uh, two components: coordinates, which is language dependent, primitives, which is language independent, and then sort of learn these Veshel style, particularly the language dependent part in a Veshel style method. Focus is another method. Here, the difference is that instead of doing a weighted average over all the existing tokens, you do a weighted average over only those tokens which overlap between the source and the new language. So that's kind of the difference. Uh, Another simple method that has been recently proposed is constrained one-to-X. So this takes a slightly different approach. So here, this makes use of the fact that the new tokens are in the convex hull of the existing tokens. So now what you do is formulate the problem of learning new token embeddings as a word-to-vec problem. So you need to learn uh, token embeddings, and you learn this in a word-to-vec style, which means you kind of do this skip gram training that you typically do in word2vec. However, with the following constraints. One, the embeddings of the existing tokens are not updated during word2vec training. And embeddings of the new tokens are strictly expressed as a convex combination of existing tokens. So just the averaging weights are essentially learned. And this sort of ensures that the word2vec training uh, uh, ensures that you get embeddings in the convex hull. Uh, but of course, how do you ensure that you are still learning some cross-lingual stuff? So in addition to the corpus, the language corpus, we also use cross-lingual mappings of dictionary entries. Basically, you get bilingual dictionary entries uh, between the source and the target language that you're interested in. Simply serialize them and add it like a sentence in a uh, corpus and add it for word-to-word training. And this very simple method is good enough to learn some cross-lingual mappings as well. Now, the advantage of using constrained word-to-vec is compared to VESHEL, etc., which were just learning static mappings, word-level mappings. Uh, Here, uh, the new embeddings also do some distributed learning using word2vec at the same time. So it's sort of a joint word2vec distributed learning for the new language as well as learning cross-lingual mappings using the bilingual dictionary entries. And we can see that this very simple technique kind of is competitive or even better than many other sophisticated initialization approaches that like VESHEL, etc., that we just saw. Uh, the other interesting method is this zero-shot tokenizer transfer that I talked about, which uses a hyper network. So the idea here is that, okay, uh, can we learn a function that can predict the embedding of any given tokenizer for a fixed language model? So you fix the language model. Now, if I just give you any tokenizer, can you predict the embedding for that? And for that, the model has to, you have to learn a function upfront, trained on a variety of tokenizers, so that given any tokenizer, it can predict its embedding. So that's the idea. I mean, if you can see this diagram, you give any piece of text and any arbitrary tokenizer uh, to this network, it can predict its embedding. And typically you have two embeddings on the input side or embeddings on the output side. So how does this work, right? So what you do is you generate a lot of synthetic data for a variety of tokenizers that can be consumed by the language model. And then the hypernetwork is trained to produce the embedding for these tokens. But the thing is, you don't know what are the goal target embeddings to train this for. Well, you don't need to know, right? So what you can do is you feed the output of this hyper network to the language model that you're interested in. So initialize the language model's input and output embeddings, and then do standard causal language model training for the language model. Uh, and in the process, as the language model is trained using causal language modeling, the hyperparameters of the parameters of the hypernetwork are adjusted so as to get the best embeddings that result in the best loss for the language model. So in a way, you indirectly train the model in an end-to-end fashion to sort of learn the best embeddings that result in best uh, uh, causal language modeling for the language model of interest. And so in a way, it's good because you're not doing end-to-end training. And unlike the other models we just discussed, where the mappings were learned externally using bilingual embeddings or dictionaries or word-to-vec, etc. Right? So here, the tokenizer transfer is directly correlated to language model performance. And this model seems to be outperforming on a bunch of languages, all the other uh, methods for tokenizer transfer without even being having specifically trained for that. So it's just trained on a lot of synthetic tokenizers, etc. So that's a bunch of work on tokenization, and there's a lot of work happening in this area. To summarize, vocab expansion is necessary to reduce fertility and it improves efficiency. However, is vocabulary expansion better than relying on the initial suboptimal vocabulary? Well, when you do continual pre-training, you do see an initial drop in results before recovery. Uh, and the amount of vocab expansion data required for getting that result back, it might vary, but uh, it's still useful. So can we do better than random initialization? So we just saw that there are a variety of methods, and uh, to summarize, simple methods like averaging or constraint word to vec are sufficient for initialization, uh, faster initialization. Uh, so will vocabulary expansion lead to lower performance on English? So a key result is that if the initialized embeddings are in the convex hull of the existing embeddings, then the greedy decoding results don't change, and therefore you can retain English performance. Now, that was the first stage of vocabulary expansion. We have our new LM, multilingual LM with new tokens initialized with some new embeddings. But one, the initialization of these embeddings might still not be well aligned to the English LM. And second, the model still has not seen a lot of data in the new language. And therefore, for these two reasons, you need to do continual pre-training. So what is continual pre-training? So it's standard causal language modeling, but with data in the new language. And you will typically train with a lot of monolingual data, and ideally you want to train document or paragraph data, whatever can fit in into the context of the LM. Training on such long coherent sequences is important so that the model can learn and correlate different pieces of information, and it's not limited to information within a sentence context. Uh, One thing to take care here is that we don't want to forget English competence and knowledge, and therefore it's important to uh, one option is to include English in the pre-training data, uh, and or two is sort of to fine tune only a small number of adapter parameters. So you freeze most of the English LM as it is, and then add a few adapter parameters, and then only fine tune these models, these parameters for data from the new language. Of course, that puts a limit on the capacity for learning the new language, especially if you have a lot of monolingual data in the new language. Uh, so let's walk through what needs to be done for continued pre-training. So the first thing, of course, is you need good multilingual corpora. So and what properties do you want to see in the multilingual corpora that you have for continual pre-training? So one, we need large-scale document-level datasets, and I explained why that is important. The documents have to be of high quality, uh, good language, good topics, etc. Wide coverage of topics. You would want to see representation of culture-specific data, native literature. These might not be there in the English corpus that the model is pre-trained on. So additional knowledge that are culture-specific needs to be represented. Uh, we need to capture data from different modalities and genres, because a lot of data for many languages might not even be available in textual format. Maybe they are in audio format. Maybe they are not in HTML but in PDF. So data from can we capture data from these different modalities so that the data is much richer and diverse. Finally, because our models are English heavy, uh, can we have some sort of augmented data to improve cross-lingual transfer? And by this, typically what this means is parallel translation data, right? So if you have parallel translation data also in the mix, maybe that can help improve cross-lingual transfer. But it's not just parallel translation data, even transliteration data can help better alignment. Uh, so typically we do have a lot of multilingual corpora, popular ones including MC4, CC100, Cultura X, MadLad, which are good starting points. We should take these corpora for uh, doing our pre-training. These typically contain large-scale document level datasets. But what we don't know about them is the quality of the documents, the coverage of topics, and they might not have culture-specific data. They might not capture. They're mostly text only and don't have data from other modalities, uh, and might not be able to do much with helping cross-lingual transfer. So the solution is sort of maybe to build custom language-specific collections of data to address these gaps, which different language groups that are interested could are better positioned to sort of build this as well. So as an example of that, I will cover the Indic LLM suite. So the Indic LLM suite builds uh, Sangraha, which is a collection of high quality pre-training data at scale for 22 Indian languages. And uh, the salient features of this, as far as collecting high quality data goes, is that one, the data is curated from high quality sources, manually vetted websites, etc. So the quality of these sources is ensured. Uh, then there is a high quality filtering pipeline to ensure high quality. So this will do things like ensuring documents with high quality of the language by using language model filters, by using various other heuristic filters to filter out bad stuff. This also this work also includes data from different modalities, from audio data, from extracted from videos or uh, audio channels from different sources, run through ASR so as to get data from these modalities that might not be present in the text are also captured. As I said, a lot of data may be logged in PDFs, and uh, PDF extraction of text from these PDFs might not be very easy because they typically you would have proprietary fonts, etc., represented. So the only way is probably to do OCR to unlock this regional and cultural content in these PDFs. And so Sangra kind of converts these PDFs using OCR into text. And these multimodal sources are also run through this high quality pipeline to ensure high quality called Setu. And that sort of results in the final corpus, one which is three components. One is the verified component, which is about 64 billion tokens from known high quality sources. Unverified sources are sources like CC100 or MadLad and CultureX, but they have been run through the filtering pipeline to kind of identify good quality documents. And finally, to ensure cross-lingual alignment, synthetic sources are created. So here, uh, a subset of this, mostly Wikipedia pages, have been translated from English to major Indian languages. Not all the 22, but about 14 languages where the translation quality is good enough. And then they have been transliterated using transliteration engines, so into Roman script. So these are available sort of for research into how translations or transliterations can make and improve cross-lingual transfer. So why do we want to do this continual pre-training with all the multilingual data that we've collected? So one is, of course, to improve language competence and fluency. So as an example here, the perplexity will decrease with increase in the pre-training corpus size. So as you train, for example, with more corpora, in this example Chinese, you can see that the perplexity drops. The second thing is that because you're training, doing continual pre-training uh, with a mix of English and the target language, that should help improve the representation similarity between the two languages. And so you can see here that the representation similarity, say between Gujarati and English for the base LLM and after continued pre-training, you can see that continual pre-training helps improve the similarities between English and the target language. Uh, so that's another very useful thing, and that should sort of transfer to better cross-lingual transfer for downstream tasks. Finally, we want to provide knowledge in the target language for better understanding, because it is kind of well studied and understood that the models presented with native language can make better use of in-language information than doing cross-lingual transfer. This is from various cross-lingual probing studies like X Factor and MLAMA. Plus, of course, the data curation of culture-specific uh, multimodal knowledge, etc., can bring in culture-specific knowledge that are not captured in the English data. And that is why you would want to do continual pre-training. So, as an example, to illustrate this limitation of multilingual models not being able to transfer from English, we can look at these knowledge probing tasks. In this case, this is an example from X Factor. So here you have these English prompts, these facts like Bloomberg LP, founded in New York. This is a tuple, and this can be serialized as an English prompt. X was founded in Y. Now the task is sort of given the uh, prefix, predict the token Y, right? So for example, the English sentence you want to predict, okay, Bloomberg was founded in, and the answer should be New York. And you have the same prompt in another language, say like Spanish. So Bloomberg LP fue fundada en, pardon my Spanish, and you would want to predict Nueva York. Now, does this prediction accuracy in Spanish and English remain the same for the same set of prompts? In fact, it doesn't. The English models performance is typically higher. The English language performance is typically higher than performance in other languages, as measured by accuracy. Okay, and so this knowledge probing task shows that uh, non-English languages don't have enough data to sort of do these predictions, uh, which is why cross-lingual transfer or having data in the native language is important. And we still have a long way to go in cross-lingual transfer as well as the availability of data. So what can we do to improve cross-lingual transfer during pre-training? So one, two directions. So one is use of parallel or translation data, and two, use of Romanized data. So why is that important? So this can help improve cross-lingual alignment. If you see if the model sees the English sentence and its corresponding translation in, say, Spanish or Hindi, the the attention models can essentially correlate translations between each other and bring similar representations across different languages closer to each other. Uh, the same holds for Romanized representation. If the model sees Romanized representation of data, uh, so typically many non-English languages do have borrowed words from English, and these can serve as anchors to sort of bring the English and Romanized representations closer to each other, and that can help to bring the English and native language representations hopefully also better, but at least the Romanized representations can be an alternative representation to the native script representation of languages. Uh, so this helps, of course, improve cross-lingual alignment, make the knowledge available in English in the target languages, and of course, translation is an important task that we would want the LLMs to do well. And so surely translation task can help. So let's delve deeper. So using translation, parallel or translated data, how does this go? So we can use parallel data in different forms. We can train on document or paragraph pairs. Of course, there is very little availability. Most of the parallel data is in the form of sentence pairs, and depending on the language pairs, the amount of data varies. Uh, what has been shown in the past is that if you incorporate this kind of empty data with different kinds of objectives with encoder LLMs, uh, they do improve translation capability, of course, but NLU capabilities only to a certain extent. Most of the gains are on retrieval tasks, cross-lingual retrieval tasks, but classification and other tasks show limited improvement. But I think this is an area that needs more investigation, more research to see how we can effectively use parallel data to improve cross-lingual transfer. Now, instead of using original parallel data, you could also use machine translated data. And the advantage of this is that given you have off-the-shelf empty models, we can generate uh, document level data for translation using translation in a target language at scale, and then you can train the model using these translated documents. Now, this will bring in a lot of knowledge into the target language itself. And this is some preliminary work that shows that, okay, if you train the model only on translated documents, you can achieve performance that is close to what you can achieve with pre-training in the native language documents. And with a little bit of native language documents, you can essentially recover all the performance. So it sort of is an encouraging sign that training on translated documents is useful. We need to better understand the impact of translation quality. We need to understand better if translating at scale, bringing a lot of data from English and translating that can help better knowledge transfer. So this is interesting directions to kind of work on. Uh, so yeah, just delving further, so we could use human written parallel data, as I said, on the document or para level, which is very limited availability. Training on sentence pairs, more data is available. So there are some results, but I think more experiments need to be done. Most of the results previously have been with encoder-only models and NLU tasks, or encoder-decoder models with NLG tasks. So how does this translated data really impact downstream tasks when it comes to decoder-only models? That's something to be studied. Uh, And use of machine translated data. This is again delving more and showing you some of the detailed results here. So if you train on, if you look at the table at the bottom, if you train on machine translated document level data, uh, if you use the Hindi model versus using all the synthetic data generated from translating from English, performance is slightly inferior, but if you use kind of 10% of the original language data, you can recover most of the performance or even be better than sort of the original Hindi data. You can just look at the last column, the average across multiple tasks. So the training on just original Hindi data is about 77% average. Training on synthetic data, you see some drop, but you can just recover it back if you just use just 10% of authentic data as well. So that's very encouraging. That's kind of an interesting area of how to use synthetic data. Increasingly, we are seeing synthetic data being used a lot, even for English LM training, data generated from other LMs. Now, how do you use synthetic data, especially synthetic data coupled with translation data, uh, to do LLM training? That's sort of a very interesting open area of work. Romanized representation has been explored. So as we already discussed, using non-Latin scripts is challenging because the fertilities can be very high, uh, and we have seen the limitations of high fertility, etc. Now, uh, if you look at this example here, right? So this is a Hindi sentence in Devanagari script as well as Roman script. Now, the Devanagari script results in 130 tokens, whereas the same LM, in this case, this is Llama 2, results in just 63 tokens for the Romanized representation. So you can see that immediately there is a drop in the fertility, which is good. And if we now say instead of pre-training on the uh, natural script, the Devanagari script, if we pre-train on the Romanized script, what happens, right? So one, of course, we already saw this fertility drop. So to give you more specific examples, on Llama 2 Gujarati, the fertility drops from 18.44 to 3 in the Roman script. For Hindi, it drops from 7 to about 3 again. For Malayalam, it drops from 12 to 5. And so you can see that there is more than 2x and sometimes even 3, 4, 5x drop in the fertility depending on the language. Not just that, but the similarity between the English data and corresponding Hindi data, the representation similarity is higher for Romanized script compared to the native script. So, in the native script, for example, in Hindi, the cosine similarity between English and native script data is zero point 0.4, whereas the cosine similarity between English and the corresponding Hindi data in Romanized script is zero point 0.5. So that's very useful to know that the Romanized representation is better aligned to English than the native script representation that can facilitate better cross-lingual transfer. So to summarize this section, uh, how much data, so CPT is surely beneficial to improve language fluency and cross-lingual transfer. How much data should be used for CPT? Probably a modest amount of data, maybe hundreds of millions of tokens, or maybe even less, is good enough for language competency and some cross-lingual transfer. But is that enough to do good knowledge transfer? So there are open avenues of how to do better cross-lingual transfer, or do you actually need to translate a lot of stuff from English and then use that for pre-training in the target language? That of course means a lot of compute, but is it really necessary, or can we come up with better cross-lingual transfer techniques? So does parallel data improve cross-lingual transfer? So yes, it does improve cross translation quality. Uh, it does improve cross-lingual transfer to some extent, probably, but this needs further research as to how we can do this better. Uh, there are data augmentation strategies like romanization, which we saw is very good at improving representation similarity. Code switching is also useful, which I'll talk about later in the context as well. Which means if you can mix the sentences with English words as well as say Hindi words, then these mixed language sentences, which are what code switch sentences, can help better align English and the other languages. What do we do about drop in English performance? So one mitigation is to sort of have a good significant ratio of English during pre-training. And the other is to use adapters for CPT, but you will still take some hit on English performance. This depends on the language model, the number of languages involved, etc. Uh, the question now is, okay, how important is it to retain English performance for cross-lingual transfer, effective cross-lingual transfer? I think that's an open question which probably needs better research and understanding. Finally, after we do continued pre-training, we have our base multilingual model, and now we need to do instruction tuning to align it to a new language. So let's see what instruction fine-tuning does. So in instruction fine-tuning, we bring in instruction fine-tune data, which are tuples of the form instruction, input, and output. Okay, so the instruction might be, okay, given this sentence, correct the grammatical errors in this sentence. So the input is the grammatically incorrect sentence, and the output would be the grammatically correct sentence. So that's an example of a typical example in an instruction fine-tuning data set. Uh, so you would want to sort of train on in-language instruction fine-tuning data set, and the training objective is typically supervised objective. So to maximize the probability of the output given the input and the instruction. And at the same time, while you are doing this to improve in-language performance, say for Hindi or Spanish, you also want to retain performance for the English task. Uh, and how do we do that? So you, again, just as we did for CPT, we would want to also have a fraction of examples in English during instruction fine-tuning. Okay, so what are the different kinds of instruction fine-tuning strategies so as to improve performance for these non-English languages? So we can break this up into different kinds of tasks that we want to do. One is we want to do we want to generate instruction fine-tuning data in such a way that cross-lingual performance improves. So we could just train on English data and hope cross-lingual transfer happens. Or two, we could generate in-language instruction fine-tune data using machine translation. Uh, and of course, if native language data is available for instruction fine-tuning, all the good. But that is typically not so the case, and so we need to do machine translation. How can we do culturally and locally relevant IFT data? How do we generate that kind of data? Of course, we have general IFT data, but then there are other auxiliary tasks which can help improve cross-lingual transfer. So parallel data translation as a task is useful. Monolingual data language modeling as a task is useful. So we'll see these in detail. Or we can transform existing IFT data sets so as to improve cross-lingual transfer. So we can use romanized forms of the data that can be useful for romanized processing. We look at some cross-lingual thought data, cross-lingual IFT data, code switching IFT data, etc. in detail, so as to understand how these techniques can help cross-lingual transfer. So broadly, the idea with these is one, to look at techniques for generating data in native language for IFT, and two, to look at a set of tasks that can enable cross-lingual transfer. So of course, let's go through this detail. So the first strategy is just to use English IFT data. There are a lot of English instruction fine-tuning data sets like say Dolly or uh, Open Assistant or Alpaca, etc. So we could just fine-tune on these instruction fine-tune on English and just evaluate on non-English data. So this is mostly zero-shot cross-lingual evaluation of these models. The other is, of course, we can take all these English data sets and translate them into your language of interest and then fine tune the model on the translated data sets. So typically, you can see some of the examples here on different tasks like Q&A tasks like Bele Bele and MQQA, and summarization tasks like Excel sum. We can see that training on in-language data is better than just training on English. So that's a strong recommendation to use machine translated IFT data. And the question is, how do we create this machine translated, this translated IFT data? So one, you could use off-the-shelf NMT models, say proprietary models like Google or Azure, or open models like NLLB, or language specific models like IndicTrans, etc. So that's one way to do it. Or you could use GPT for doing the translations. So the off-the-shelf models are typically higher quality, particularly for low resource languages. GPT, uh, the quality is lower, as we saw for low resource languages, might be at par for high resource languages. But the good thing is they can take larger context of entire paragraphs and translate them, which might be good when translating these IFT datasets. Or we can do a hybrid approach. So depending on the language, for some languages we could use GPT, whether GPT translation quality is good, or use off-the-shelf NMT system for other languages. And you can see this choice clearly depends on the translation quality, and the tables below basically show that translation quality mm, is better in general for low resource languages across a large number of languages for the NMT systems, but at document level, maybe there is a case to be made for using the models like GPT for translation. Okay, now, okay, once you've decided what engine to translate, what do you want to translate? So you have a choice of one, you could translate instruction, input, output, everything using uh, the translation model, or you could choose to keep the instructions in English. And this is because the models are typically good at English instruction following, and a lot of use cases you would still write the instructions in English. So keep the instructions in English and just translate the input and output in the target language, which is what Bloomsy does. Uh, One thing to do is quality filtering, because translation systems are not perfect, and we want to retain only high quality examples for instruction fine tuning. So you could use a MT evaluation metric like Comet QE uh, or Comet Kiwi to identify bad translations and filter them out. You could also use rule-based filters. Maybe you just don't want to include code examples in the translated IFT data. It's just difficult to translate code examples with code, etc. Another approach that is typically used is to translate only the instruction and the input, and then use a language model to essentially generate the response. The reason to do that is maybe the language model has better context, larger context to work and translate, and maybe the language model, GPT, etc., might have some culture specific understanding to generate culture specific responses. So that might be a reason to just not use the outputs from the IFT dataset to do the translations. Or you might basically have access to a large set of prompts which you can translate and then use GPT to basically do the uh, translation, response generation. The other way is to sort of use some seed instructions, generate some entire native language examples, uh, uh, and then use a language model like GPT to generate entire examples from uh, in the target language itself. So this is just like the uh, alpaca or the self-instruct approach to automatically generate diverse examples, instruction fine-tuning examples in the target language directly. So this can help generate culture-specific examples, but quality diversity might be an issue depending upon the quality of the ability of the language model to generate these examples. Okay, so far, but we have just been looking at translating existing data sets, or at least partially translating existing data sets. This might not be reflective of the topics relevant to language users. So can we come up with methods to actually generate instruction fine-tuning data sets that are relevant to the culture, to the language, etc. And here I think creativity is the limit. There are lots of approaches people are trying out uh, to generate culturally relevant examples. I'll just pick up one illustrative example from the English LLM suite again, where multiple English LLMs are used along with Wikipedia context to simulate conversations in a topic of interest for that particular culture or language, right? So, for example, here uh, uh, a conversation about Delhi, the history of Delhi, tourism in Delhi, etc., is generated. So, what is done is there is an LLM which acts as an intent LLM and generates an intent, given a Wikipedia page. So, the intent might be understanding the history of Delhi. Then there is another, the LLM in another role uh, acts as a user and generates a question relevant to that intent. So, for example, who was the ruler of the Delhi Sultanate, given the Wikipedia page and the intent. Then there is another LLM, an LLM acting as an assistant, which now given the Wikipedia page and the question, will generate the answer. Okay, and then we can just have the LLM also play the role of the user again, but now with next user LLM, which has the previous conversation context, and then it can generate a new question. Okay, and now you can go back and forth between the next user LLM role and the assistant LLM role and keep generating a conversation, right? So now starting with the Wikipedia English page, we have generated a conversation relevant to that culture uh, or region, uh, simulating a conversation. Now, we can translate this entire conversation into another language. We just discussed how we can go about translating IFT data. Right? So, for example, on the right-hand side, you can see an example where you have a conversation about the Lotus Temple in Delhi that was generated using this approach. This data set is called WikiChat, and this is then translated into Telugu. So you have a Telugu IFT data set with topics that are relevant to the Indian context available for instruction fine tuning. Uh, so we can also use parallel data, parallel corpora for instruction fine tuning. So here we define translation as a task for uh, uh, the model, right? So translation is a special task because it teaches one the model to translate, which is an important cross-lingual task, but it also sort of helps to align English and language representations better. And there is some work to show that, okay, if you use translation as an IFT task, it has benefits for other tasks also in downstream tasks. So if you see the table at the top, for example, uh, you can see that uh, including say English Chinese task improves Squad, MLQA, MLAMA, and Excel sum as well, right? So both the parallel data and the translated IFT are sort of complementary to each other. If you have both of them, that also helps. So that's also some results at the bottom that you can see. Uh, so, uh, so there are many uh, language models that are being specifically trained for the translation task as well. For example, the ALMA and the Tower models that are being specifically trained for translation, and you can see that translation performance improves for these language models. There are also approaches that, uh, in addition to standard translation tasks, you might want to uh, include related translation tasks like, okay, translate, but with formal, informal tone, with formal tone, or with a male gender speaking or a female gender speaking, these kind of instructions, or translate, but use simple language in the target language. So that's another line of work which I'm not covering much today, but that's also interesting. Like translation with all its varieties is also an interesting task for LLMs to do, which typically standard translation models cannot do. So let's go to the next task. So we might also want to use monolingual data, a task involving monolingual data during instruction fine tuning. This is a bit strange because we have already done contingent pre-training. So why do we want to include a monolingual data task? Well, the reason is this. If you have observed so far, we have been doing instruction fine tuning data on a lot of translated data. Now, the translated data is not like typical language. The output from the models might not be fluent, even if they are for fluent and high quality. The translate the outputs from translation models are not as diverse as natural text, and therefore the output that you get from an IFT model trained on translationese kind of IFT data might not be as rich, and therefore it's important to expose the model to native monolingual data also during IFT. And to do that, you can incorporate a task that helps the model generate fluent text, right? So if you already have IFT data in the native language, then of course there is no issue. But if you're relying more on translated data, then a task of this sort can help. And so the task can be something as simple as sentence completion, right? Uh, so you could have something like complete the following sentence in Indonesian according to its context. You give a prefix, and the answer is the continuation of that sentence, right? And so it's very easy to get a lot of monolingual data and repurpose it for this sentence completion task. That's a very simple way to fold in a monolingual task into the IFT framework. Of course, you can always kind of switch between instruction fine tuning and causal language modeling, but that's a little bit more complicated. That's task one. Task two, a sentence completion task, can be very easily integrated into the standard IFT pipeline. It's shown that that is useful. Now, if you want to work with Romanized representation, as we saw, Romanized representation is better aligned than the native script. So then, just like pre-training, we can convert all our IFT data into Romanized representation and instruction fine-tune with Romanized data. So in this case, uh, your English IFT data would be translated as well as Romanized before doing the fine-tuning. So here, the results kind of show that continual pre-training with Romanized data is first crucial before you do instruction fine-tuning with Romanized data. And NLG performance increases on a bunch of tasks, including machine translation. And NLG performance is sort of on par. You don't get a lot of benefit, but there are efficiency gains for sure, right? So there is a case for using Romanized representation. Okay, so far we have looked at instruction input-output pairs in the target language. But earlier on we saw that the models implicitly think in English. So can we make use of that fact to improve cross-lingual performance? So one way to do that is you create your prompts in such a way that you ask the model to first think in English and then respond in English, right? So you have a so the standard way to do it is monolingual QA. So ask the question in Chinese and ask the model to answer in Chinese. Instead of doing that, we've now give the input in Chinese, ask the model to think in English and then respond in Chinese. So the model then does the interpretation in uh, English, the chain of thought reasoning in English, and then raise response in Chinese. So this is sort of inspired from the chain of thought reasoning, but now the thinking is happening in English, and you ask the model to explicitly do the thinking in English so that the model can then generate the answer better and then generate it in the target language. Now, of course, this is kind of, well, you could say that you could just first translate the input into English and then pass it on to the English LLM and then get the output and translate it back. In this case, all that is happening implicitly. So multiple inference calls are avoided. Right? You might otherwise have to kind of first do translation, then do uh, the LLM processing, and then translation again. Right? So here a single inference is doing everything. Also, yeah, the translation uh, in the input, the original input in the original language is also available to the LLM. So if even if there are some translation errors, the model sort of may be able to look back at the original, can look at the original input also while doing the processing. The limitation, of course, is that this increases the token length for the model because now this additional generation in English is also involved, and therefore it reduces the longest possible sequence uh, addressable. Okay. Now that was about prompting, but you could do the same thing during instruction tuning. So now you created instruction tuning data in such a way that there are English instructions, English rationales or thought also generated before generating the output in English. Okay, and so that's how you fine tune the model with this kind of instruction fine tune data, which includes English thought data. The limitation, as I said, is that now you're limited in the maximum sequence length that is possible. But this is useful. This kind of cross-lingual thought data is multiple couple of works that they show that this kind of instruction fine-tuned data can be more beneficial than using standard instruction fine-tuning data with input and output language. Now, can you sort of overcome this limitation of including implicitly English data? So one approach is sort of, okay, I don't always have to have the same input and output language, right? So I can, if you have English data, in-language English data, and you have also its translated version. You can mix and match. So now we can have a question in English, answer in Hindi, or question in Hindi and answer in English to create cross-lingual instruction datasets. Now, this kind of cross-lingual instruction datasets, you can kind of jointly now optimize for all these tasks. So English tasks, in-language tasks, cross-lingual tasks jointly. And that sort of facilitates some cross-lingual uh, instruction, uh, cross-lingual alignment, and helps the model to do better than if you are training only on language specific data. Now, this is sort of not really use explicitly using English generation, but it's been shown that this can be a good proxy for the kind of cross-lingual thought data in English that we saw earlier, and can uh, bridge the gap between that kind of cross-lingual thought data while not needing as long a sequence generation as cross-lingual thought prompting. Mm. Next approach is to use code switch instruction tunings, right? So if we have some part of our instruction fine tuning data where we replace, say, the questions in the native language with their some of the words with their English equivalents, now the model sort of is seeing code switch data and can do good correlation across uh, languages, right? And so code switching uh, can help the model align better at the sub-sentence level. And some optimizations here that have been done. One, when doing code switching, retain the English instructions, because the models, as we said, are good at understanding English instructions. Code switch only on the inputs and maybe the outputs. Uh, it might also be good to do code switching during pre-training as well. That's been also shown to be useful. Okay, another thing that we could do, and this is not necessarily relevant to multilingual context, but even in English context, is to use self-distillation from the language model itself. So instead of using the responses in the data set that we have, which was human curated or maybe synthetically generated from some other LM, take the question and then ask the language model itself to generate the response. And typically, it's been shown that the model is better at learning from its own self-generated responses. As an example here, the question is, what is the most important time management technique? And you might have a gold answer, which is minimize distractions to maintain focus. But if you ask the same language model to generate a response, maintain focus by minimizing any disturbance. That's what this language model that you are interested in generates. And that the model can do a better job at learning from this kind of its own responses. So that's another useful technique for improving the model. Now we can put all these together. So we can have our vanilla SFT trained on just English instruction pairs. We can include translated data. We can include the self-distilled instruction pairs where you use the model's own responses and then translate them. And then you can use cross-lingual instructions as we talked about. So question in English, answer in, say, Japanese or Hindi, include translation tasks, include to sort of improve cross-lingual alignment, include sentence completion tasks to improve uh, language generation abilities. So that native language competency is retained because you're using a lot of these translated data sets. So if we put all of these together, uh, there is a work that sort of puts all of these ideas together. And if you compare it with only translation or only translating the source, only translating the target, this mixture of objectives on an average works out to be better on the target language while also retaining performance in English, maybe even improving the English performance to some extent. Uh, So these ablation studies kind of also show that using the LLM's own responses is useful. Um, the MTN sentence completion tasks are also useful. Cross-lingual instruction tuning and code switching, all these have kind of different benefits. Another study also shows that translation task is useful. Training on cross-lingual thought data is effective. Cross-lingual instruction tuning, while not as effective as cross-lingual thought data, still can close the gap with cross-lingual thought data. So we've seen a bunch of these techniques for multilingual instruction fine tuning. So to summarize what we looked at, machine translation is the dominant technique to create IFT data. Uh, and we can be creative, we can use the English LLMs to generate culture specific, region specific data before translation, IFT data before translation. There are a bunch of techniques to improve alignment between English and other languages using things like cross-lingual instruction tuning, thought data, romanized or code switch data, etc., which we should use to sort of improve multilingual performance. Machine translation is an important task which should be included in the multilingual IFT mix. Now that brings us to sort of the end of the major sections in this tutorial. And to summarize what we kind of looked at, we see that there are rapid advances happening in the multilingual LLM world. Some recent English-heavy models are also having better tokenizers for non-English languages like Gemma 2 and Llama 3. They are having better data representation mixes for uh, non-English languages, but still there is a gap between the English performance and other language performance, and therefore a lot of these techniques that we discussed today about continued pre-training, vocabulary expansion, and work on uh, work on instruction finding in a multilingual setting is important. Uh, so extending strong English LMs is interesting and is going to be important going forward also, because English LMs are going to be at the frontier and it's easier to catch up by doing these adaptations rather than training multilingual models from scratch. Vocabulary expansion is important to make these LLMs efficient, but there are challenges in achieving coherence, convergence, and there are interesting problems around this area. Continual pre-training is important, and how do we improve cross-lingual transfer during continual pre-training? There are interesting directions around that. A lot of work has gone into aligning languages at the instruction fine-tuning stage. So going forward, what are interesting areas to work on? So broadly, the holy grail is to sort of how do we improve cross-lingual transfer and different ways of doing that. How to use synthetic data, synthetic plus translated data. How do we make the models think better English? We have some insights on where, in what parts of the model are doing the thinking in English. So how do we improve this, use that information to improve thinking in English? Uh, can we now many of these models are good at English, and fine tuning them for new languages might also be a kind of expensive process. But can we compose like the task solving abilities of the English LLMs, maybe have smaller LLMs for language skills, and then compose these abilities to have an ensemble which works on for different tasks better on a new language. Uh, there are small language models coming up, but then can we have small multilingual models which combine, which while the models being small can make effective use of capacity in a multilingual setting as well. There is very little work on multilingual preference optimization. So how do we collect preference data for multiple languages, and how do we optimize for preferences in multiple languages? That especially being sensitive to culture specific knowledge is interesting. So there are some initial efforts around that for collecting multilingual preference optimization data using a mix of multilingual synthetic data, synthetically generating preferences also using LLMs. So there's some work, but this is very nascent and this is interesting work to work on. So some of these works I will include in the bibliography so that you can go ahead and dig into it further. On the data and resource front, how do we scalably evaluate multilingual LLMs? There are not enough benchmarks, uh, and how do we come up with multilingual benchmarks? Uh, these days, it's very popular to use LLMs for evaluation for English, and they have shown some success, although there are questions about even English evaluation, but uh, it's gaining adoption. Uh, how do we do the same for using LLMs for evaluation of multilingual LLMs? Uh, a lot of the data is in English. How do we unlock collection of large-scale culture-specific text corpora, or maybe data in other modalities as well, so as to be more inclusive, diverse in our data sources, and be more responsive in a more sensitive way for specific languages, cultures, etc. So these are all interesting directions. So with that, I will conclude this survey, and thanks for listening in. This PDF will be available. Uh, there is a GitHub page as well, which will capture the content of these slides, bibliography, and going forward, some code on vocabulary expansion, continued pre-training, instruction fine-tuning with all these strategies, etc. So finally, I would like to acknowledge a lot of my colleagues. This tutorial is based on work, explorations, discussions with a lot of my colleagues at AI for Bharat and at Microsoft. So you can feel free to look at the GitHub page for more details or contact me for any questions. Thank you. With that, I'll end this tutorial.